Hello, everyone. Today, we will continue discussing our topics in analog electronics class. The topic of today is the bipolar junction transistor. So, what is the bipolar junction transistor? The operation, the construction, and the characteristics. So, we will discuss all of that in our class. So, the objectives today are understanding the physical structure and operation of the bipolar junction transistor, and also investigating the characteristics of this bipolar junction transistor for both NPN and PNP devices. So we will see the construction, what the meaning of having NPN or PNP devices of a BJT. Also understanding the characteristics of a bipolar junction transistor, and understand and become familiar with the DC analysis of a BJT. So these are the objectives of our class today. So like any semiconductor material, guys, we need firstly to start from the basics of the construction and operation, then do some analysis, find some relations, and provide or drive the characteristics, and then see how can we make a mathematical model and DC analysis for this type of semiconductor material. So let's start firstly with the construction. Firstly, guys, as you can see, the construction of a BJT is, you can see here in this figure that, just a moment to connect this. Okay. So, okay, yeah, so it's here. So as you can see in this figure, guys, we have three terminals or three layers in this semiconductor material or this semiconductor device. We have, for instance, on the left-hand side, this is the NPN type. So we have N type semiconductor layer. We have P semiconductor and N semiconductor layer. So we have three layers here. In the right-hand side, it's another type of the BJT. We have also three layers, P type, N type, and P type. So since we have three P, N, and P, or NP and N semiconductor materials, so we have two depletion regions. Between the N and P here, we have one depletion region. Between the P and N, we have another depletion region, and the same is also for the other type. The names of these layers will be, the first one is called collector, another one is called base, and the third one is called emitter. So we have three layers. It could be NPN and PNP. So also we have here collector, we have base, and emitter. So what are the features of these layers? So if we start with the distribution of these layers, you will find that two outer layers and one intermediate layer or middle layer. So the outer layers are called collector and emitter, and the middle layer is called base. Okay, so again, whatever NPN or PNP types, the two outer layers are called collector and emitter, here or here, and the middle layer is called base. Okay, what are the features of every layer? So starting with the emitter. So emitter is highly doped semiconductor. Highly doped means the minority carriers are too much compared to other layers. So it will allow excessive current to flow, since we have high doped semiconductor material. So this is the emitter, which is the one of the outer layers. For instance, this is the one here in the NPN transistor type. And here also, this is the emitter here in the bottom side. So this is the high doped semiconductor layer. The collector is moderate doped semiconductor material. So it's less than the emitter, but it's not very less. So just moderate doped semiconductor material. And it's also one of the outer layers. And the middle layer, which is the base, is very small layer in terms of the thickness. So in terms of the thickness, this is very small layer. And at the same time, it's a lightly doped semiconductor material. So these are the features of the BJT, whatever NPN or PNP type semiconductor switches. So what will happen between the three layers and what the function of every layer in the transistor? This is what will be investigated in this class. So according to that, guys, since we have BJT now with equivalent to anti-series connected diodes, you know that if we have just one diode, we have two modes of operation, of two possibilities of operation. So the diode can be on or off. But since now we have two anti-series connected diodes, so here, guys, since we have, for instance, on the right-hand side, we have P and N, so I can consider this as a diode like that. So this is here the collector, and this is the base. And then we have the base to emitter. It's another diode like that. So this is the emitter. And this represents now PNP transistor. On the left-hand side, I have N to the top, P to the bottom of the first junction. So this is collector, this is base, and then we have the opposite diode like that. So we still have two anti-series diodes. All of the time, guys, anti-series diodes, if you have two diodes like that with this configuration on the left-hand side or the right configuration on the right-hand side, any of these will not allow a current to flow. Because if you apply to collector and emitter whatever polarity of voltage is, one of the diodes will be in the opposite or reverse biasing. So reverse biasing means it will just allow to have a saturation current. So this is theoretically what we have if you have two anti-series diodes. But since we have the middle layer, we have a terminal to the middle layer, so this will have some interactions in the operation, and we will see this together. So again, we have now like two diodes. So for the two diodes, guys, since we have two operations for every diode, so we expect to have here 4 possible operations or connections of the operation or modes of operation of our transistor. The different modes of operation are, let's imagine together now, guys, we have here NPN transistor. NPN transistor, so we have junction number 1 between emitter and base, junction number 2 between base and emitter, and this is the symbol of the NBN transistor, collector, base, and emitter. So since base is P and emitter is N, so we expect that the current is going to flow in this direction. Okay, so we have here this arrow, which means the current direction. So this is NPN type. If it is PNP type, this arrow will be reversed. Okay, so this arrow will be reversed. Okay, let's understand firstly the different modes of operation now. Now assume, guys, we have 4 different cases. 4 different cases means actually the relation between the applied voltages, because we mentioned, guys, the 2 diodes can be forward or reverse. So we have 4 different combinations, depends on the applied voltages, the base to collector and base to emitter. Okay, so these are the factors or the voltages that will control the operation of our transistor. So we have here 4 quadrants, VBC and VBE. It could be positive or negative. So having VBC positive means the base is positive compared to collector. But VBC is negative means the collector is positive to base. Or if I say VBC is positive, so this means VB is greater than VC. And if I say VBC is negative, so this means VC is greater than VB. So this is the meaning of VBC positive or negative, and the same is also for base to emitter voltage. So the first case is if you have VE and VC less than V base. So if the V emitter to V base or the V collector to V base are less than 0 or negative, so this means our transistor is working in the cutoff mode. And cutoff mode means no current is going to flow. So this is the cutoff. Let's have a different color here. So this is the cutoff operation. The second mode of operation is the saturation mode. Saturation mode, if VE is less than VB, so V emitter is less than V base, or VC is less than V base, which means the polarity of the supply is like that. In this case, what will happen is we will have a saturation. We will have saturation. Saturation because, as you can see, this is N and this is N. This is this is P-type material, the base, and this is positive. So this will make our transistor connected in saturation and having very small current flow. So this is called saturation region. Okay. And the third mode is actually, it's not only one mode, but it's going to be 2 different modes. What are the 2 different modes? If V base is greater than V emitter but less than V collector. So this is going to be called forward active. Or V base is greater than V collector and less than V emitter. And this is going to be called reverse active. And in both of cases, these will be active regions. These will be active regions, and we call it forward active or reverse active. Later on, we will elaborate more in the different modes of operation and see the application of every mode. So let's start, guys, with the active mode, where As you can see here, we have V base to emitter, positive, and we have V collector to emitter, to base is positive as well. Okay, so in active mode, the base to emitter junction is forward. Can you see here, guys? This is a base, it's P type. This is the emitter, it's N type, and B is connected to positive, N is connected to the negative of this supply. So this means this is going to be a forward biased connection. So for the forward biased connection, guys, what will happen? What will happen is the depletion region, the junction of base to emitter, is going to be forward biased. And forward biased means it's allowing a current to start flow. However, this is positive P, and we still have here the collector is connected to positive, which means this junction here, the base to collector, is in reverse bias. Why it's reverse bias? Because the volt between the collector and base is positive connected to the N type, and negative of the VCC is connected to the base, the P type. So this means the other junction here, the base to collector junction, is reverse biased. So this means the first diode here is on and the second diode here is off. What will happen? Let's investigate what will happen according to the features we discussed about the layers. We mentioned that the emitter layer, guys, so here is the emitter layer. The emitter layer is heavily doped or extensively doped layer, which means it has a lot of minority carriers. So if you apply the V base to emitter like that, emitter is connected to negative and base is connected to positive, so VB is positive, what will happen is this junction here, this junction will be very small resistance and will allow a current to flow. So as you can see here, the electrons will start flowing between base and emitter. Okay, nice. So this is the first part. The second part is the move the excessive electrons to the base layer will break the collector to base junction. So again, here, since you have high excessive current flowing right here, so you will have excess of a lot of free electrons move to this base layer. Okay, so you will have a lot of access of the electrons to this region here, and this will press on this depletion region. Okay, since you have external effects from the excessive electrons here, what will happen is the moved excessive electrons break the collector to base junction. So the second junction here, guys, will be broken because of the excessive electrons came from the emitter side. In this case, once you could break this junction and you have already possibility to move a lot of electrons, so once this junction is broken, so a flow of high value of current or a lot of numbers of electrons can go to the collector side right now. So the idea, guys, is if we consider just we have P, N, and P, or N, P, and N, we may not have a current flow. However, because of the different layer excessive electrons or heavy doped material, this will allow more electrons to be there, and this will break the other junction. So this is the reason why this type of semiconductor material is working. So mainly the doping of the different layers. So again, emitter is excessively doped, the collector is moderate doped, and the very small layer of the base is slightly doped. So this is the features of our three layers in the BJT switch or BJT transistor. Okay, so this is the operation, guys. This is the nature of the operation. So once the base to collector junction is broken or became very small resistance, a high current will flow between the collector and emitter. Still, because the base layer is very small layer, it will not allow very high current to flow to the base terminal. So most of the current will flow in the from the emitter to collector, or the electrons will move from the emitter to collector, which means the current is flowing from the collector to emitter. You know that current is flowing against the electrons direction. But for the base current, still we will have very small current because it's very slightly doped semiconductor materials. Okay, nice. So this is the features and operation of the transistor in the forward active. Now, based on this operation, guys, we need to drive some relations for the currents of the BJT. So, start firstly with the base layer. We agree that base layer is slightly doped, very small layer. So we agree that the current is going to be relatively small. And for the collector and the emitter currents, since it's heavily doped or moderated doped, so the collector is moderate and the emitter is heavily doped or excessive doped semiconductor material, so we expect that a heavy current can flow between these two terminals. So in this case, guys, we can say that the emitter current, which is going to flow from the emitter to inside the transistor. So we can say now, since the BE junction is like a regular diode, so it will have the BE current, which is the emitter current, and this BE current, like the diode current, can be represented as I emitter equals IE-O, which is the saturation current of the PN junction, times E to power VBE over VT, and VT is the thermal volt, minus 1. And actually, since VBE is much large compared to V thermal, so this is going to be greater than unity, and we can say that this relation is approximately equal IE0, or saturation, times E to power VBE over VT. So this is the emitter current relation with the base to emitter volt. And this is nothing but a PN junction diode current. Again, VT is the usual thermal volt. At room temperature, it's 0.026, if I'm not mistaken. This is the constant value. And IEO is the saturation current, or we call it here the multiplying constant, or the zero current in the beginning, which is in range of 10 to power minus 12 to 10 to power minus 16 ampere for this type of transistors. So this is the saturation current of the BN junction. Okay. Now, What about the collector current? So to a first approximation, the collector current is proportional to VBE over VT. Why? Because actually the BE volt is the reason of the excessive electrons that provide this current. So still BE is the main volt that will allow a current to flow, the base to emitter volt. Okay. And is independent of the reverse biased BC volt because still BC is reverse biased. So it's not affecting the collector current. So the device looks like a constant current source. So in this case, guys, we can say that the collector current is controlled by VBE. So we can consider like VBE now is the controlling volt of our transistor. You remember in case of MOSFET or FET, we had the VGS, the gate to source, was the controlling volt, which will provide the electric field that will allow more drain current to flow. So by the same way here, but here we don't have electric field effect, so it's not field effect transistor. This is bipolar junction transistor, so it's not working by means of electric field. It's working by means of the difference or the potential difference between the base and emitter. So it's depends on the voltage difference between base and emitter. It's not electric field. So once you have this BE volt, this will control the current flow in our collector. So we can say that it's controlled switch device by means of VBE. So in this case, guys, we can still say I collector also is a function of VBE divide VT. So it's still IS times E to power VBE divide VT, where we can say now that the emitter to collector currents are related by this ratio. So since the emitter current is the main current and I collector will be a part of this current and the remaining current will flow in the base, so we will have a factor here called alpha, and this alpha is expected to be very close to unity. Why? Because the base layer is very small layer and the current flow in this terminal will be very, very small. So the parameter alpha, guys, we call it here common base current gain. Common base current gain. Okay? And it's less than unity because all of the time, if you apply just Kirchhoff current law, so I collector will be a part of I emitter, so it has to be less than unity. So we can also write this relation right now. So since I collector is a function of I emitter, so we can say the saturation current of I collector is a function of the saturation current of the emitter as well. So we can say IS here in this relation is equal to alpha times I emitter saturation value. Now regarding the base current, I think by Kirchhoff current law now we can get this current. But let's just investigate the current we have here for the base. So we can say that I base will have two components. So this is the base current. We agreed that the electrons will flow from the emitter to the base here, okay? But still, you will have some holes moving from the base to the emitter layer. So we can have two components actually of I base. One component due to electrons and one component due to holes. And these components depends on the VBE, and it's called non-contributing current or contributing current in the collector. So IB1 is non-contributing current, and IB2 is contributing current in the collector. But by the end, we can say that apply Kirchhoff current law, you will get I base as a function of I emitter and I collector. So we can say by the end, still I base is a function of VBE over VT. So the same voltage ratio is affecting the base current. However, we expect to have very small operator here in this relation because I base is very small due to the very little number of majority carriers in this semiconductor material. So if we say now this constant is going to be IBO, we expect IBO to be very small value. Let's now compare the three currents of this transistor. So if this is our transistor, here we have the VCC, we have resistance connected to the collector, so we call it RC, and we have here VBB and a resistor between the supply and base terminal, and this is NPN transistor. So we have I base flowing here, I emitter is connected to ground here, so this is common emitter, and I collector is going to flow from the collector to emitter like that. If you apply Kirchhoff current law, guys, we can say that I emitter equals I base plus I collector. Okay, so here we can say I emitter equals I base plus I collector. So this is applying Kirchhoff current law at this transistor or this node in the transistor. So starting firstly with IB, we mentioned that IB equals IBO, so this is the base saturation current times E to VPE slash or divide V thermal. And also IC, we have IS VBE, E to power VBE divide V thermal, and we mentioned that, or if we relate the collector to base currents, so we will have another factor here called beta, and beta is called common emitter current gain, common emitter current gain. So in this case, we can say now IB, and this is the relation of IB, equals IC divide beta, which is IS divide beta times E to power VBE divide VT. So what's the value of beta? Let me firstly erase. So what's the value of beta in this relation, or range of beta in this relation? Actually, beta is in range between 50 to 300. It depends on the semiconductor material doping. Okay, so this is the common emitter current gain. Okay, common emitter current gain. So we had before the common base current gain. So if we compare now the different relations, guys, firstly apply Kirchhoff current law. So we can say now I emitter equals I collector plus I base. So we have I collector equals beta times I base. If you substitute this here in this relation, so we can find that I emitter equals I base plus beta I base. So it would be 1 plus beta times I base. So we can say also I collector as a function of I emitter equals, from here, guys, you can get I base and substitute I base equals IC divide beta. So in this case, you will get I collector. Let me make this step with you to show you how this relation came. So we said that I emitter equals 1 plus beta times I base. And we mentioned that I base equals, from this relation, I base equals I collector divide beta. So I can say here, this is 1 plus beta divide beta times I collector. So I can say now I collector equals beta divide 1 plus beta I emitter. And we mentioned that, guys, beta is relatively high value, which means now beta divide 1 plus beta, so it will be very close to unity, and this is actually the alpha. So this is the relation between alpha and beta. So if beta is 100, for instance, so the alpha is going to be 100 divided 101, which is around 0.99 or very close to unity. So this is the relation now, guys. So we can say now the collector current is very close to the emitter current value. And the difference is just the base current, the small base current in our circuit. Okay, guys. So this is the relation between the different currents and the common emitter current gain, beta, and common base current gain, alpha. So what we discussed now is the NPN type. So this is the NPN transistor. What about the PNP transistor? So the PNP, the current will flow in the opposite direction. So the I emitter will be divided into I beta and I collector. Still, I emitter is the largest current because this is the highly doped layer, but just the current directions have been changed. So a summary for our relations now. So we can say that I collector equals I saturation EVBE divide VT, and I emitter equals I collector divide alpha, and I beta equals I collector divide beta. For the PNP transistor, so we can replace the VBE by VEB. So I collector is also I saturation times VEB e to power VEB divide VT, and still I emitter is equal I collector divide alpha, and I beta equals I collector divide beta. Sorry, I base equals I collector divide beta. Both of transistors, you can apply the same Kirchhoff current law relations. So I emitter equal I collector plus I base all of the time. You can replace I collector by beta times I base. So in this case, the I emitter will be 1 plus beta times I base. And by the end, alpha equals beta divide 1 plus beta, or beta equals alpha divide 1 minus alpha. So these are the relations of our transistor in case of NPN or PNP. Some questions just to refresh your knowledge. So multiple choice question. In NPN bipolar junction transistor, the collector current is relatively small compared to the base current. So this is the first choice. A bit less than the emitter current, a bit higher than the emitter current, no right answer. Okay, so we mentioned that all of the time the collector current is a part of the emitter current and the base current is very small, so we can say that it's a bit less than the emitter current. So this is the right answer. Let's solve this numerical example together, guys. So here in this example, we need to calculate the collector and emitter currents given the base current and current gain. So here we have beta is given 150 and the base current is given 15 microampere, and we will assume that the transistor is forward active mode, the same mode that we already discussed. So it's going to be very straightforward substitution in the equations we have. So these are the equations we have, guys. We just summarize these equations so we can use it right now. So we can say now I collector equals beta times I base. We have beta is 150 and I base is 15 microampere. So this would be now 2.25 milliampere. I'd like to get I emitter. So I can say that I emitter is equal 1 plus beta times I base, or I can say it's I collector plus I base, the same. So if you substitute here, it will be 2.27 milliampere. So the difference between them is only the I base. If you now calculate the factors, so what is the alpha? So alpha is nothing but beta divide 1 plus beta. So 150 divide 151, which is 0.9934. Okay, so this is a very straightforward example, just substitution in our equations to understand the concept of the three currents of the BJT transistor. Now, guys, like any transistor, we need to see the characteristic. So assume that we have our transistor right here, and we need to give the output characteristic. And the output characteristic, guys, is going to be the relation between the collector current and the V collector to emitter. Since V base to emitter is the controlling volt, so the collector to emitter, the volt is going to be controlled, and the I collector also will be controlled. So we call the IC versus VCE as the output characteristic. So firstly, we can say, guys, IB, the base current, versus VBE is referred to as input characteristic. And IC versus VCE is referred to as the output characteristic. We agree together that VBE is controlling the operation. So for VCE greater than VBE on, if the V collector to emitter is greater than VBE on, so this means the collector to base junction is reverse bias and the collector current equals the emitter current. So in this case, guys, this will be the shape of our characteristic. So for VCE, any value for VCE greater than VBE, and VBE on is nothing but the turn on volt of the PN junction. So it could be 0.4, 0.7 up to the semiconductor material. So once this volt, the collector to emitter volt is greater than VBE on, so this means you will have a collector current flowing. And this current is going to be a small current because the V is very small. Okay. Now, if the collector to emitter is less than the turn on volt, so this means the collector to base junction will be forward biased. So again, if the collector to base, this volt, is greater than, sorry, the collector to emitter, this volt, is greater than VBE. So this means the CB, the collector to base junction, is going to be forward biased. And if it is forward biased, guys, so we expect that our current will decrease to 0. So in this case, you will find that in this portion of the relation, the current is reducing to 0. So this is now the collector current versus VCE at very small VBE. And the current of BE is very small. Now, if you increase the base current, so we expect to have now higher current flow. So in this case, with more base current, we will have multiple characteristics like that. And again, you will have now this active mode characteristic and this part of linear mode characteristic. So the forward here is the saturation, and this is here the linear mode of our transistor. So this is the collector current versus VCE of a BJT transistor. As we mentioned earlier, guys, in the MOSFET, the saturation current is not a completely constant relation. It has slope. So the same is also here for a BJT. We have a slope, which means we have output resistance. But again, this output resistance, we care about this output resistance in AC analysis, not in DC analysis. And the intersection with the negative VCE here will be VA, the early volt, early access or volt. So this volt is approximately between 50 to 300 volt of this transistor. And the slope of this curve is 1 over R equal VA divide I collector. Okay, so this is the exact characteristic if we consider the slope of the characteristic that we have. Now, let's move to a part of the analysis of our transistor. So the analysis is nothing but converting the transistor to an equivalent circuit and make some mathematical representation for the transistor. So if this is our transistor, guys, so this is called common emitter transistor. So the VCE is the volt between collector to emitter, the VBE, the volt between base to emitter, and in this box here is our transistor. And we connect these to a resistor and VCC here from the collector side, and to another resistor and VBB from the base side, and the emitter is connected to ground. So this is common emitter circuit. How can we represent or get equivalent circuit? Actually, it's very easy because we can say that from the base to emitter side. So the base to emitter is nothing but a diode. So the VBE here will be just a turn on volt through a diode. This is for the part of the circuit here on the left hand side. So this is loop number 1, and here this is loop number 1. For the second loop right here, the VCE is the collector to emitter volt, and we have a collector current flowing here. And then the emitter is connected to ground. So the emitter is connected to ground is here. Now, we can replace the part of this piece of the circuit here by this dependent source. So we will have a VCE, and at the same time, this VCE depends on the current flow on the circuit. And the current flow here is the collector current, which is nothing but B times I base. So we have I base actually flowing here, and we have here dependent source depend on this base current. So this is a mathematical representation of our transistor. So we can say here, guys, if you apply now any circuit analysis, so from the circuit here, we can say that In the first loop here, I can say VBB minus VBE on divide RB equals base current. And this is the first relation. And the second relation is the transistor relation, which is I collector equals beta IB. So once we get IB, beta is given for any transistor, so I can get the collector current. So if I get the collector current, I can use it now in the other circuit here. So I can say now VCC equals ICRC plus VCE. And from here, we can get the value of VCE. Okay, so this is the circuit analysis we need. If you would like to get the circuit loss, the transistor losses here, so we can say that it's equal to two pieces of losses actually, from the base side and from the collector side. So from the base to emitter and from the collector to emitter. In more detailed model, we call that this term of loss is equals the gating loss or driving loss, which depends on the pulses applied to the base to emitter. And the other one here is called the conduction loss because it depends on the current flow on the transistor itself. Okay, so the total loss is going to be I base times VBE on plus I collector times VCE. Actually, VBE on is very small, and IB is very, very small as well. So the majority of the losses here will be in the part of IC times VCE, which is the conduction loss. So we can say that the total loss is approximately equals I collectors times VCE. Okay, but exact calculation, we can consider both of terms right here. Now, let's solve this example, guys, to see the DC analysis of that transistor. So for the circuit shown, guys, the common emitter BJT have the following parameters. VBB is given 4 volts. The RB is 220 kilo ohm. The VCC is 10 volt. The R collector given is 2 kilo ohms. And VBE on is given 0.7 volts. And beta is 200. And we need to calculate the currents and VCE in this transistor. So this is our equivalent circuit. If you would like to draw it, it's fine. If not, it's very easy. You can just work from the circuit right here. So starting firstly with I base, guys. So from this branch here, I can say that this volt equals the current plus RB plus VBE on. So I can get IB as 4 volt minus VBE divided to 20 kilo ohms. So this is the first step. We got IB. The second step is use the transistor relation to get the collector current. So the transistor relation is nothing but I collector equals beta times IB. So beta is 200. You calculated I base, so you can calculate now the collector current. Once you have the collector current, you can get the emitter current, which is collector current plus base current, or 1 plus beta times IB. So this will provide you with the value of the total current. Okay, now for VCE, take care, guys. Just one important note is so if we consider the Kirchhoff current law here, so IB plus I collector, so you have 15 microampere plus 3, so it's gonna be 3.015. Here we have 3.02. Why? Because actually we have some approximation in our model. Okay, so and as we mentioned, we have the base current, we have contributing current and non-contributing current. So instead of using Kirchhoff current law, please use this relation here. So we can say all the time I emitter is 1 plus beta times I base. Okay, so this is more realistic because we have some assumptions in the circuit. Okay, so please use this standard relation for the current in our circuit. Okay, the difference is going to be very minor, but we do prefer to use the same relation as in the textbook. For the VCE, now we can use this loop right here. So VCC is 10 volt, RC is given 2 kilo ohms, so I can say now 10 volt equals 2 kilo ohms times I collector, which is calculated, plus VCE. So we can get the value of VCE from this relation here. So VCE is going to be 4 volt. Now, for the power dissipation, you can add the two terms of the power, IB times VBE on. So 15 microampere times 0.7 and 3 milliampere times 4 volts. So we will have 12 milliwatts. Okay. Actually, even if you consider this here, he considered that, but by the end he just multiplied 3 times 4 because this part is going to be very, very small contribution for the power loss. Okay. So this is a numerical example for the DC analysis of the common emitter bipolar junction transistor. Now, guys, you are ready to solve and make analysis for the BJT. So this is our homework. You need to solve these two questions. So the first question is, verify the results of example 5.3 with the P-SPICE analysis. So we have the example, the previous examples we had. So please provide the results using P-SPICE, and in this case, repeat the analysis for RB equals 180 kilo ohm and 260 kilo ohm, and what can be said about RB limiting the base current. So how RB is limiting the base current. You need to compare between the results. So the same example we solved it right here. You need to repeat this example with different values of RB. Instead of 220K, you need to apply now 180K and 260K and see the results. And please provide all the wave forms along with numbers. Okay, so this is for the simulation using P-SPICE. The other question is, for this circuit, guys, you have VCC is given 3.3 volt, VBB is 2 volt, R collector is 3.2 kilo ohm, R base is 430 kilo ohm, transistor parameter beta is given 150, and VB is 0.7. You need to calculate the following parameters. What is I base, what is I collector, and V collector to emitter, and the dissipated transistor power. So please submit this homework by the next week on Tuesday. I will make this assignment on eCampus. So a summary, guys, for what we have discussed today. So we learned the construction of the BJT, the operation of a BJT in forward active mode, the output characteristics of common emitter bipolar junction transistor, the characteristic of a BJT, the DC equivalent circuit, and the DC analysis of common emitter bipolar junction transistors. Thank you so much, and see you in next classes.